All right. Good morning, everyone. Welcome. Almost there. Almost at the end of the semester, but also apparently of times. If you are local in Winnipeg, hope you stay safe. We're supposed to have a very, very large snowstorm. Um, it's April, but Winnipeg does not care. So, and if you are not in Winnipeg, enjoy the lovely weather. Okay, so I don't have a warm-up question for you today because I'm busy getting set up. Yeah, it should be fine. You've lived in Winnipeg for a while. You should know how to deal with snow. But just stay at home as much as you can and be safe. So let's do a warm-up problem together. So let's let A be the set 1, 2, 3. And so several parts. What is the size of A cross A? How many functions are there from A cross A into A? So this is a closed binary operator. And then C, how many functions from part A from part B rather are commutative. So let's take a look at this together. Let's remind ourselves when I say A cross A, which I can also write as A squared. This is a set, it's a set of ordered pairs, A1, A2, such that A1 and A2 are both in A. So let's list out the elements of A cross A in this case. What are some elements of A cross A? 1, 1. That's definitely in there. 1 and 1 are both elements of A, for sure. 1, 2. 1, 3. And 2, 1. There we go. Okay. So from here, I think we can fill out the rest. Crucial ideas are you're allowed to have the same number twice. It's not a set. It's an ordered pair. So A1 and A2 are completely separate. They don't know about each other. And order also does not matter. You can have 1, 2, and 2, 1, or maybe it does matter. 1, 2, and 2, 1 are different elements. So the rest of the elements then should be easy enough to come up with. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. So we can answer part A now. How many elements are there in A cross A? What is the size of A cross A? Yeah, 9, right? We got 9 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. There they are. And satisfyingly, mathematicians love writing down statements like this. The size of A cross A is equal to the size of A times the size of A. Right? There are 9 elements in A cross A. There are 3 elements in A. 3 times 3 is 9. And that's not a coincidence. Right? We can do this with a rule of product process. How many ways are there to pick A1? Well, I pick any element of A. There are 3 elements of A, so 3 ways to pick A1. And then picking A2 is completely independent from A1. I have another 3 ways of picking A2. So 3 times 3 gives me 9 elements of A cross A. Okay. Now, how many functions, how many closed binary operations from A cross A into A? Well, the way to think about this one is we've got our set A cross A over here and our set A over here. How many elements in A cross A? We know that there's 9. How many elements in A? We know that there's 3. And how does it work? Well, I'm trying to create a function. I'm trying to come up with a function f, which means from each one of these 9 elements, I need to draw exactly 1 arrow into A. So I want to do a rule of product process. I need to know 2 things. How many steps are in my process? And how many options do I have at each step? So I want to draw an arrow from here to here. That's 1 step in my process. How many steps and options per step? Three options, 9 steps. Good. 9 steps, 3 options on each step. This is step 1. I've picked for element maybe 1, 1. We'll put that one first. I've got 3 options. 1, 1 can be equal to 1. 1, 1 can be equal to 2. Or 1, 1 can be equal to 3. 3 options for that one. 3 options for the next one, the next one, the next one, the next one. So, putting that all together, how many functions are there? It's definitely one of these 2 numbers. It's definitely either 9 to the 3 or 3 to the 9. So let's see, 9 to the 3. Let's look at both of these and try and work out which one we want. 9 to the 3 is 9 times 9 times 9. And 3 to the 9 is 3 times 3 times 3 times 3 times 3. There's 9 of these in total. So we got to figure out which one of these is a process with 9 steps, 3 options at each step. Think about the rule of product calculation. How would that work out? This would be step 1 has 9 options, step 2 has 9 options, step 3 has 9 options. This one is step 1 has 3 options, 2 has 3 options, 3 has 3 options, all the way up to step 9, which has 3 options. So we do want 3 to the 9 here. Easy mistake to make. Got to be careful about those because these 2 things are not equal to each other. All right. How am I going to fit this all here? Just barely see part C up at the top. Great. So these are all functions, not just the commutative ones. Let's remind ourselves of what I mean when I say commutative. So a function is commutative if the order I do the inputs doesn't matter. If f of a comma b is equal to f of b comma a. What it means to be commutative. So if I go back to this 9-step process, let's look at what the process was. I wanted to figure out what f of 1 comma 1 was. I had 3 options. Then I figured out what f of 1 comma 2 is. Then f of 1 comma 3. then f of 2 comma 1, f of 2 comma 2, f of 2 comma 3, f of 3 comma 1, 3 comma 2, and f of 3 comma 3. Those were my, oops, I'm off the bottom of the page. Those were my 9 steps, each of which had 3 options. Let's try and do the same process, but now I want to build a commutative function. How many options are there for f of 1 comma 1? Got to pick something in A. Yeah, all right, still 3 options. This can still be 1, 2, or 3. All of those are fine. So I've still got 3 options at this step. How about f of 1 comma 2? Still 3 options, right? F of 1 comma 2, that can also go to 1, 2, or 3. 3 options, still good. 1 comma 3, where can I send 1 comma 3? 3 options, right? Still good here. This can still go anywhere. It's not until I get to f of 2 comma 1 that things change. According to my commutative formula, what is f of 2 comma 1 equal to? It's equal to f of 1 comma 2. I can swap the order and the answer doesn't change. That's what commutative means. So if I already chose f of 1 comma 2, how many options do I have for f of 2 comma 1? Not 3 anymore. Now I'm down to just 1 option here. There's just 1 option here because I already made the choice. I had 3 choices when I chose f of 1 comma 2, and that forced f of 2 comma 1 to be the same thing. So if I picked f of 1 comma 2 is equal to 2, I can pick any value, 1, 2, or 3. They're all fine. But once I pick a value for f of 1 comma 2, f of 2 comma 1 has to be the same value. They have to line up in order to have a commutative function. So only 1 choice here. How many choices for f of 2 comma 3? Sorry, f of 2 comma 2. I'm back up to 3 choices, right? There's no restrictions on f of 2 comma 2. Nothing that came before it was already chosen. What about f of 2 comma 3? Yeah, right? Also 3 choices. No restrictions yet. Nothing's forced it one way or another. What about f of 3 comma 1? I'm back down to 1 choice. F of 3 comma 1 has to match f of 1 comma 3. I already picked f of 1 comma 3 up here. Fixed a value for it up here. Now it has to match. F of 3 comma 2, same thing. F of 3 comma 2 has to match the value I picked up here. I only get 1 option there. And then f of 3 comma 3, I got 3 options again. Completely unrestricted. Commutativity doesn't affect f of 3 comma 3 because there's only 1 way to have 3 show up twice. So now, rule of product, multiply these numbers all together. How many commutative functions are there from A cross A to A? 3 to the 6. Can I explain this one again? Yep, totally. So I've got to pick values for each one of these 9 inputs, right? I've got 9 inputs in A cross A. For each one of them, I got to draw my arrow over to 1, 2, or 3. So let's do it. Let's pick some values. What should f of 1 comma 1 be? Pick a number, 1, 2, or 3. Can't pick wrong. 2. 2 is a great choice. F of 1 comma 1 is equal to 2. That's where that arrow goes. Where's f of 1 comma 2? Where's that going to go? Three. Sounds great. Anybody can chime in. Can't pick a wrong answer. Any number you pick is good. F of 1 comma 3. 1, 2, or 3? 1. Sounds great. When I get to f of 2 comma 1, suddenly I can't pick any number anymore. Suddenly my options are restricted. Because I'm commutative, the order of my inputs is not supposed to matter. So f of 1 comma 2 and f of 2 comma 1 have to line up. So we got to choose freely here. We picked 2, we picked 3, we picked 1, right? Just picking numbers because we liked them. Now that I get to 2 comma 1, I have to match what I chose already. This one has to be equal to 3. I can't pick anything else. Back in part B, again, I could pick anything I wanted. 1, 2, or 3, completely free, no restrictions. But if I want it to be commutative, I have to follow the commutative rule. Order can't matter in my inputs, which means f of 2, 1 and f of 1, 2 are linked to each other. So this has to be 3 again. I only have one option this time. So we can keep going. F of 2 comma 2, I pick 1. That seems like a good output for me. F of 2 comma 3, I'll pick 2. Seems like a reasonable output. F of 3 comma 1, it's commutative. Order doesn't matter. It's got to match f of 1 comma 3. I don't get to make any decisions. My decision was already made. This has to be 1 again. Same thing for f of 3 comma 2. It's got to match my previous choice. F of 3 comma 3, though, I get a brand new choice. Why are we not adding the options with 1? We're saying all the numbers we can get are commutative. Why are we not adding the options with 1? I'm not sure I follow the question. Yeah, we're not. So, right, this is the number of options I have. Rule of product says we're going to end up multiplying all of these numbers together. Right, this is my 9-step process. Step 1, step 2, step 3, step 4. Before, I always had 3 options. All of these were 3s. That's how I got my 3 to the 9. But now, some of them are down to 1. Is it always equal to n to the k minus n, where n is the number, n to the k is the possible number of functions? No. The number of things that are fixed will change with n. It's a really good question. I really like Kurt's question. If the size of A is equal to n, then how many, we could ask the same question, same series of questions. What is the size of A cross A? This one's relatively straightforward. Not n to the n, just n squared, right? Because I have n options for the first one times n options for the second one. I've got this A cross A is size of A times size of A going on. So I'm going to get n squared options there. How many functions are there from A cross A to A? Well, I have an n squared step process with n steps, with n choices at each step. So I'm going to have n options, n options, n options, n options, n squared times. So this is going to be n to the power n squared. It's a big number. And now here's the hard question. Here's what Kurt's asking. How many of these are commutative? And this is going to be the one that's a little bit trickier to answer. I'm going to do it a little bit quickly just because I don't want to spend all day on this. If I look at my grid of values, and here's 1, 1, here's n, 1, 1, n, n, n. I always get free choices along the diagonal. Along the diagonal, I don't have to worry about commutativity. So there's always n options with n choices. And then anything below the diagonal has a matching pair above the diagonal where I just swap the order. So commutativity says I get to choose this top triangle and that's going to fix or determine this bottom triangle. This is determined by commutativity. So up here, I'm always going to have n choices. Down here, I'm only ever going to have one choice. It's going to have to match what happens when I swap it. So now, here's the question. How many things are in this triangle? And the easiest way to answer this is that everything in this triangle has two different values. How many ways are there to pick two different values if order doesn't matter? Right, because it doesn't matter if I pick the small one first or the big one first. I only get to make the choice once. So I might as well say I chose the small one first. How many things are in this triangle? How many ways are there to pick two elements out of n if order doesn't matter? N choose 2. Exactly right. There's n choose 2 things in here. So how many steps of my process actually have n choices? I have n choose 2 in this top triangle plus n along the diagonal. So in this case, my answer is n to the power n choose 2 plus n. And then even more quickly, we can do a little bit of arithmetic. N choose 2 plus n is equal to n times n minus 1 over 2 plus n is equal to n squared minus n over 2 plus 2n over 2. Combine these together, I get n squared plus n divided by 2. And you can see that n squared plus n divided by 2 is smaller than n squared. We can figure out exactly what the difference is. It's n to the n squared minus n squared over 2. And then I need to add back an n over 2, which I'm going to write like this. So it's not that I want k minus n, it's that I want n squared minus this value. And that'll give me n squared plus n all divided by 2. This is a very difficult question, and I've done it a little bit quickly because there's more stuff I want to talk about today. Okay, how are we feeling about that one? Anything I can say again, anything I can go over again? I know something like that came up on the quiz. I thought that we'd talked about all these concepts in class. It might be a little challenging, but could put it all together. But based off of questions I saw in office hours, it looks like maybe this was a little harder than I had anticipated. I wanted to make sure we talked about it, dove deep. Okay. Gonna move on then. Next topic. Okay, so we talked a little bit about what it means if you have an injection or a surjection between sets. So let's just recall what we said. If I have a set of size A and a set of size B, and I have an injection, F from A to B is an injection, what can I say about the size of A and the size of B? B is greater than or equal to A, right? Or A is less than or equal to B. Size of A is less than or equal to B. A fits inside of B, maybe with some room to spare, or maybe not. Maybe it fits in snugly. But if I have an injection from A to B, then B has to have at least as many elements as A has. Okay, and let's do the opposite as well. Let's do a surjection. If I have a function from A into B and I hit every value in B, sometimes more than once even, F from A to B is a surjection, then what can I say about size of A and size of B? Yeah. Then B has to be less than or equal to A, or A has to be greater than or equal to B, based on the way I've written it. If I have a surjection, that means every element in B gets lined up with at least one thing in A, maybe more than one. But for every element of B, there's at least one element in A that gets mapped to it, which means I have at least as many elements in A total as there are in B. And then one last question, if I have a bijection, size of A to size of B, everything lines up perfectly, 1 to 1, and onto. Every element in A has exactly one element in B that gets paired with it. Then what do I know? Then A has to be equal to B. Okay. This is all review. We've seen all of this before. Just wanted to keep in mind, completely unrelatedly, he lied, separate question, which are there more of? Even numbers or odd numbers? What's the domain? Let's say the domain is in all integers, including the negative ones. Equal. All right. Why equal? Why does it seem like equal is a reasonable answer? I like the answer equal. Equal makes sense to me. Why? Why does equal feel good? For every number, there's a next even number. Every other integer is either odd or even. This one I really like. Owen's got an answer I really like. For every n that's an even number, I know n plus 1 is always odd. I'm going to pick out this one, because I like it a lot. Not on, pick out. So if I let e be the set of even integers, and O be the set of odd integers, then the function f that maps an even integer into an odd integer by f of e is equal to e plus 1. This is a bijection. Let's prove it's a bijection. Let's do that rigorously. Proof. In order to show that this is a bijection, I need to show two things. I need to show that it's an injection and a surjection. So let's start with an injection. To show it's an injection, I need to show I can't have two even numbers mapped to the same value. So let's say to see that f is an injection, assume that f of e is equal to f of d. Okay. Then e plus 1 is equal to d plus 1, because that's what my function does. Or e is equal to d. So if my outputs are the same, that means my inputs were the same. Therefore, the only way f of e is equal to f of d is if e is equal to d. So f is injective. Every output only comes from one input. If you picked two values and ended up in the same place, that means you must have started in the same place. So f is an injection. And now I need f to be a surjection. Choose any odd number let's say m, then m minus 1 is even, and f of m minus 1 is equal to m minus 1 plus 1. Oops, I'm off the bottom of the page, which is equal to m. So m is in the range of f. And since m was arbitrary, every odd number is in the range, and that means the range is equal to the codomain, that means F is a surjection. Arbitrary F is a surjection. Okay. So, which are there more of, even numbers or odd numbers? It makes sense to say they're the same, because there's a bijection between them. Right? Bijection means the two sets have the same size. There's a bijection between even numbers and odd numbers. So, there's infinite of them, but it makes sense to say that there's the same number. All right. Anybody unhappy with this? Does this make sense? Or are we good with it? Okay. What I'm going to do now is ask a question, and then we're going to take our 2-minute break. And during the 2-minute break, just in the back of your head, I want you to think about your answer to the question. Which are there more of? Integers or even integers? That's my next question. Don't answer right away. Take your 2 minutes, go off, get a drink, get a snack, stretch. We'll come back 9:12 and we'll answer this question. Are there more integers or even integers? I'm also going to go get a drink. I'll be right back. Okay. Let's gather back around, refocus. Which are there more of? Integers in total or just even integers? Very confidently. Integers. Right? There must be more integers because this is a subset of this. Every even integer is an integer, but not every integer is an even integer. Next answer, are they maybe equal? So Earl, why'd you say maybe equal? Equal question mark. Same way as for odd integers. So what function do you recommend looking at? (2n) for even. So Earl's got this crazy idea that the number of integers and the number of even integers would be the same, even though, how could that possibly be true? Right? Even integers are a subset of integers. This is a subset that's not equal. Crazy idea. And yet, we look at the function, f of n is equal to 2n. This is a function from the integers into these even integers. And I claim f is a bijection. Let's prove that. Claim that f is a bijection. F is an injection. How do I check that? Because if f of n is equal to f of m, then 2n is equal to 2m, which is only possible if n is equal to m. So we've got the same situation as before. The only way that two outputs can be equal is if the two inputs are equal. So for all m and n in the integers, f of m equals f of n implies m is equal to n. So f is injective. Now I'll show that f is surjective. Let k, let's say, equal to 2 times j, be an even integer. Then f of j is equal to 2j is equal to k. So k is in the range of f. And since k was arbitrary, that means f is surjective. So I have a function. It's injective and surjective. That means it's a bijection. We said if you have a bijection, the two sets have the same size. So that means the number of integers and the number of even integers are the same. There's a bijection between even integers and all of the integers. They line up 1 to 1, even though it's a strict subset. So what we're discovering is that infinite sets do not work the way we expect. Here's the lesson. Here's what we learned. If A is a subset of B, so in particular, A is not equal to B, it's a subset, it's a strict subset, but A and B are still infinite, it is possible that, and now I'm going to write this in a different color and in quotation marks, size of A equals size of B. The reason I wrote this in quotation marks is that when we defined sizes of sets, infinite sets were different. We didn't really define the size of an infinite set. What we said was, oh, well, you know, if it's not finite, then it's infinite. But that's different than defining a size. And now we're seeing why. Right? Sizes and infinite sets just, they don't really go well together. They don't line up in the way we want, because you can have a strict subset, but you can still have this bijection. And because of that, we need a different idea. And so what we actually say is A is comparable to B. This is the symbol we're going to use. They have the same size or the same cardinality. So cardinality is like size, but we allow for infinity as well. So the cardinality of a finite set is just equal to its size. Cardinality and size are the same for finite sets. But when we're talking about infinite sets, we can have two infinite sets. They're both infinite. They have the same cardinality, even though one is a strict subset of another. So let's do some more examples. I claim that the cardinality of the integers is the same as the cardinality of the non-negative integers. Again, does not make sense for finite sets. This is a strict subset of this. What I'm doing is I'm claiming if I look at a number line and I start at 0, and I'm just looking at the positive integers, the non-negative integers, I can line these up 1 to 1 with all of the integers, including the negative ones. Here's my plan for how I'm going to do that. 0 is just going to go to itself. And I'm going to have my negative numbers map to my odd numbers. So -1 is going to map to 1. And -2 is going to map to 3. And -3 is going to map to 5. And I'm going to keep going like that. And then my positive numbers are going to map to my even numbers. So 1's going to map to 2. 2's going to map to 4. 3's going to map to 6. And so on. And this is my plan. So that is all to justify the following function, f, which goes from all integers just to the positive ones, or the non-negative ones. F of z is equal to, if z is greater than or equal to 0, I'm going to go with 2z. And if z is negative, first I'm going to make it positive, then I'm going to double it, then I'm going to subtract 1. Okay. And so you can check this function is matching what I'm doing up here. 0 gets doubled to 0, 1 gets doubled to 2, 2 gets doubled to 4, 3 gets doubled to 6. And so the positive integers are taking care of all the evens. The negative integers are going to take care of all the odds. -1 times -2 gives me 2. Subtract off 1, I'm at 1. -2 times -2 is 4. Subtract 1, I'm at 3. And so I'm hitting every number exactly once. So I'm not going to actually prove this. I'm not going to go through all the details. This is the function that makes that work. Pause here. Questions? How are we feeling? Okay. Let's do something even more ridiculous. Claim the integers have the same cardinality as z cross z. So just want to point out how this is, what I mean by this. Z cross z is the set of ordered pairs. I've got 0, 0, 0, 1, 1, 0, 2, 2. Right, I'm looking at this integer grid. And I'm claiming these two sets have the same cardinality. In order to do that, I need to give you a bijection from the integers into the integers squared. Again, I'm going to use a diagram to explain what's going on here. 0 is going to map to 0, 0. And then I'm going to spiral out. So 1 is going to map to 1, 0. 2 is going to map to 1, 1. 3 is going to map to 0, 1. And I'm just going to keep following this pattern. I guess what I'm showing is this non-negative integers, because I'm starting at 0 and working outwards. And you can see this pattern is going to keep going forever. It's going to hit every number exactly once. Every pair of numbers exactly once. Nothing gets missed, nothing gets left out, and so on. And since I have a bijection from the integers to the positive integers, and I have a bijection from the positive integers into this integer squared, I can chain those two bijections together. So if this is f, if I call this function g, we talked about composing functions. G composed with f is a function where you input an integer, you get a non-negative integer, and then you input that non-negative integer into G, and you get out a pair of integers. And since this was a bijection and this was a bijection, we showed that if you compose two bijections, you got a bijection. So this is proof that the integers have the same cardinality as the integers squared. There's a bijection from this set to this set as well, going through this intermediate thing. Gonna take things a step further. Gonna say something crazy now. Claim the number of integers, the cardinality of the integers, matches the cardinality of the rational numbers. Just want to pause for a second on what this claim is. This is claiming 0, 1, -1, -2, 2, whole numbers. There's the same number of them as there are fractions. 1 over 7, 412 over 819 billion. Those I'm claiming are the same. This is getting out of hand, I agree. This one's a little bit harder to show with a picture. And actually, I want to show a different technique. So if we all go all the way back to where this all started, we said if there was a bijection, then the sets had to have the same size. We later extended that to the same cardinality. But we also had this rule of injection and surjections. Well, I'm not going to give you a bijection between the integers and the rationals. I'm going to give you an injection and a surjection. Because if I give you an injection, that means that there's at most as many integers as there are rationals. And if I give you a surjection, that means there's at least as many integers as rationals. That's my plan. Rather than just give you a bijection directly. I get to give you two different functions, one of which is an injection and one of which is a surjection. All right. Who wants to be the hero? One of these is really easy. I need an injection and a surjection. So this is the one-to-one. This is F from this into this. And then I also need a surjection. G. This is onto. One of these is really easy. Who can give me the really easy one? Either a one-to-one function or an onto function. Let's take a step back, see if we can figure out which one should be easier. Yeah, so one-to-one should be easier. N goes to 1 over n is one-to-one. We can do even easier, though. Same idea, but reverse it. How do we take Ashley's idea? N over 1. My function f is really simple. F of z, f of z, z over 1. This is an injective function. I'm taking an integer, I'm giving you a rational number. I'm just dividing by 1. I think hopefully no arguments here that this is an injection. Basically, I'm saying, hey, you know how the integers are a subset of the rational numbers? Well, I'm just doing equality, basically, because they're a subset. So this one is nice and easy. This is an injection. It's 1-to-1. If f of y is equal to f of z, then y over 1 is equal to z over 1. Y is equal to z. We're good. Those are definitely an injection. The surjection is a lot harder. What I'm actually going to do with the surjection is say, you know how I said, recall that there is a function, let's call it h, from the integers into the integers squared. That's a bijection. I don't have to put a question mark there. So let's say that h of z is a comma b. My g of z is going to be a over b. And let's even make it b squared plus 1 or something. No, I want to be careful with that. Let's say a over b if b is not equal to 0 and 0 otherwise. I just want to make sure that I'm defined where this h of z is equal to a comma b. So this part's a little bit messy, but what I'm saying is there's the another very fancy term, if you want to sound fancy, is equinumerous. The integers are equinumerous with the integers squared. There's the same number of integers as there are pairs of integers. So I'm going to take my integer, turn it into a pair of integers in a bijective way, and then I'm just going to turn my pair of integers into a fraction. And I claim that this is a surjection. Yes, I am going to get a is equal to 2, b is equal to 1, and a is equal to 4, b is equal to 2. And 2 over 1 and 4 over 2, those are the same number. This is not a bijection, but it is a surjection. I do make every fraction at least once. In fact, I make every fraction infinitely many times. This is definitely a much more complicated proof in a complicated subject. But I'm claiming I have an injection and a surjection, and that means that the integers and the rationals have the same cardinality. Okay. What's the next set I should look at? Done integers, done rational numbers. Which one's next? Real numbers. Got to think about real numbers. So, which would be more surprising to you at this point? I don't know why that's a capital S. Are the real numbers, do they have the same cardinality as the non-negative integers? Right, so far, here's what we've seen. Let me summarize what I've got for you. This is not the exact order I've done things, but the even numbers are equinumerous with the non-negative integers, are equinumerous with all of the integers, are equinumerous with the squared integers, are equinumerous with the rational numbers. can I add the real numbers to this list? Or are they going to be separate? Which one do you expect? Do you just have no idea at this point? I'm curious. Because here's the thing. If there is a bijection, you won't be surprised either way. If there is a bijection, that means there's as many integers as there are real numbers, any decimals you can think of. But if there's not, that would mean that there's different infinities. That would mean, right? So maybe let's go back and look at these another way. What I'm really saying is, well, this is infinite and this is infinite, so even though this is a subset of this, they're both infinite. And if you say it that way, it's like, okay, fine. So that's why they're the same cardinality. It's infinite, there's just infinity. And, no infinity is bigger than another infinity. Maybe I can make sense of that. But if now this is not true, that would mean that some infinities are bigger than other infinities. Which is why it's really surprising that these are not the same. There is no bijection between the real numbers and the integers, the non-negative integers. And I'm going to prove it. There is no bijection f from the non-negative integers into the real numbers. It's impossible. Can't do it. Here's my proof. By contradiction. Assume, for sake of contradiction, that f from the non-negative integers into the reals is a bijection. Now I want you to think about what a function from the non-negative integers into the reals looks like. I know f of 0, f of 1, f of 2, f of 3. It's just a list. All I'm saying is that I can list out the real numbers. My contradiction is that I can list out all the real numbers. So I've got f of 0, f of 1, f of 2, f of 3, and so on. And each one of these is supposed to be some real number. So maybe f of 0 is 0. That's a real number. And f of 1, let's say it's pi. And f of 2, let's say, is the square root of 2. 1, 4, blah, blah, blah. And f of 3 can be 7, for all I care. Right? I have a list of real numbers. Here's how I show f is not a bijection. I'm going to find a number that's not on the list. Okay, and here's how I do that. The first thing I do is I'm going to extend all of these numbers so that they all have infinite decimals. And then here's what I'm going to do. My number, let's call it k, is defined as follows. The kth decimal place, or the nth decimal place is a 4 unless the nth decimal place of f of n is 4, in which case I have a 5. So my number looks like 4, because this has a 0, 0.4, because that's a 1, not a 4. But then this one is a 4, so I have a 5 instead. And then this one's a 0, so I'm going to go back to 4. And I'm going to keep going in that way. I always have 4s, unless I would line up with a 4 in the same place, in which case I want a 5 instead. And here's the thing, k is not on this list. It can't appear on the list. If it did, which position is it? If it did, then there would exist some integer n on my list with f of n equal to k. But this n has a different value in the nth decimal place. But nth decimal of n, of f of n, does not match k. So these two can't be equal because they have a different decimal value. Right? This is if f of n has a 4, then k has a 5. And if f of n doesn't have a 4, then k does have a 4. And so what I've done is I've gone down the list along a diagonal. And I said I'm not in the 0th position because I disagree at place 0. I'm not in the 1st position because I disagree at place 1. I'm not in the 2nd position because I disagree at place 2. I'm not in the 3rd position because I disagree at place 3. And so this is called a diagonalization proof. And it shows that there cannot be a bijection from the non-negative integers into the reals. The reals are a bigger infinity than the non-negative integers. Okay, so I'm going to stop there because I'm out of time, but hopefully that is surprising to everyone. I know it was the first time I learned it. Okay. Stay safe, everybody. See you on Thursday.